Hi there, I'm Jeremy Krug, and in this video we're learning about the basics of equilibrium, chemical equilibrium here in AP Chemistry, General Chemistry. Now, if you are in an AP Chemistry class or in a General Chemistry class, you're going to learn about equilibrium. If you make it all the way through AP Chemistry and you have never learned about what equilibrium is or how to write an equilibrium constant, there's something wrong. You haven't really been in an AP Chemistry class, because chemical equilibrium is one of the largest concepts that is discussed in AP Chemistry. So you really need to know about equilibrium in order to pass that class and pass that exam. So let's talk about what equilibrium is in this video. Now, as we've learned in the past, a lot of reactions in chemistry are just irreversible. That means that they can go in one direction and they can't really go in the other direction very easily. Here's an example of that. Let's say we have a nice truck here. We can see how it looked at one time. Well, over the years and decades, here is that truck, and we see that it has rusted. The iron that was in that truck went through a process of oxidation, didn't it? This is a redox reaction like we've learned in the past, and it reacts with the oxygen, and we have iron 3 oxide, which is rust. Now, we can't imagine that rust going in the opposite direction and turning into this nice new car, right? Now, we can scrape the rust off and repaint it and restore it, but we can't really cause the reaction to go in the reverse reaction. This is a reaction that, for all practical purposes, is irreversible. It only goes in one direction. Now, let's take a look at an example of a reaction that is reversible. Now, let's say we have some hydrogen and we burn that in oxygen, to make water. And if you've been following my channel, if you've subscribed, maybe you've already seen this reaction, because I carry out this reaction on my channel at least in 2 videos on my YouTube channel. And here's an image of one of those other videos where that hydrogen is just exploding, it's burning in a big fireball. But you can do the opposite as well. You can take some water, and if you have some electricity, you actually can cause the water to be turned into hydrogen and oxygen gas. And here's an example of that happening, where you take basically a 9-volt battery and immerse it into water, and you can see that the gases are forming at those 2 electrodes there. So you can have a reaction go in one direction, it can go in the opposite direction. It's reversible. Now, in chemistry, here's how we write that. We just write it like this, where we write the reaction, and then we use this double-headed arrow here to show that the reaction is reversible. It can go in both directions. So you can have the forward reaction, where you're making water out of the hydrogen and oxygen, and then the reaction's going in the opposite direction. It can reverse sometimes, and you can take the water and make hydrogen and oxygen. So it goes both ways. It's a 2-way street, as it were. Now, what does equilibrium look like in a closed system? Well, let's imagine that we have this diagram here, or this reaction rather, where we're going to take hydrogen and chlorine gases, and we're going to react them to try to make 2 hydrogen chlorides out of that. So here we have a diagram, and I have arranged these so we have 7 hydrogen molecules and 7 chlorine molecules. Now, if we think about what this is going to look like afterwards, you might think, well, you have 7 hydrogens and 7 chlorines. It's a 1:1 to 2 mole ratio. So you would expect there to be 14 molecules of HCl at the end. Well, let's see if that's actually what happened. We can actually see that that's not what happened. If we actually start counting up the molecules, we see that we only have 12 molecules of HCl. There's still one molecule of H2 and 1 molecule of Cl2. What that means is this reaction did not go to completion. We did not use up all the reactants and turn them into products. That's what happens in a reversible reaction. We don't always use up the products until there are no more. we have it going both ways. So there's still a mixture of reactant with the product in there as well. So that's what it might look like in a closed system. Now, let's try to put this in terms of numbers, because sometimes when we say chemical equilibrium, students still have a pretty tough time visualizing this. So let's illustrate this in terms of something that students might be able to understand perhaps a little bit better. And let's imagine it in terms of a dance. Let's say that you go to a dance like a prom or a homecoming dance or just some party that you're at. And let's say that there is a big dance. Let's say that there are 300 people that show up at this dance. That's a pretty big dance, at most schools. So if that's the case, we know that before the music starts playing, that nobody's dancing. But there are 300 people they've paid their money, they're in the gym, they're in the building, but they're not dancing yet. Well, let's say that we have a little observation and that we've observed that as this dance progresses, that after every song that's played, 30% of the people that are dancing will move off of the dance floor and they'll sit down. And then we also find that after every song, 20% of the people that are not dancing will get up and move to the dance floor and start dancing. And we find that this happens after every song. So how is this going to affect the number of people on the dance floor? Well, let's do the math and see. So for the first song here, we have 30% of 0. Well, that's 0. But 20% of 300 is 60. So that means we're going to have 0 people that will sit down and 60 people that will get up and start dancing. Now that's a net movement of 60 in the direction of the dance floor. So that means for this first song, we're going to have 60 people dancing, and this side will go down by 60, so that's 240 that are still sitting down. And this is going to happen after every song. So 30%, this time is 30% of 60, which is 18 will sit down, and then 20% of 240, which is 48, will get up and start dancing. So we can see those are our numbers. That's a direction of, if you subtract, that's a direction of net 30 in the direction of the dance floor. So this side will go down by 30, this side will this side will go up by 30, and this side will go down by 30. So we're down to 90 and 210. And this is going to happen again. So 30% of the dancers are going to sit down, so that's 27, and 20% of 210 will get up and start dancing, so that's 42. So we can see that there's a direction, or a net direction, of 15 in the direction of the dance floor. So that means this side will go up by 15, 105. This side goes down by 15, 195. So hopefully you see how this is going. Now, this is going to happen again. After this song, 30% of the dancers are going to sit down. So 30% of 105 is 32. And then 20% of 195 will get up and start dancing. That's 39. So we can subtract and see that the net change is plus 7 in the direction of the dance floor. So the people that are dancing will go up to 112, and the not dancing goes down by 7, so down to 188. It happens again. So after this next song, 30% of the dancers will sit down. So 30% of 112 is 34, and then 20% of the people that are sitting down, or the wallflowers, will get up and start dancing. 20% of 188 is 38. So the net change is plus 4 in the direction of the dance floor, and I guess minus 4 for the sitting down or the not dancing side. So this side, the dance floor goes up to 116, the not dancing goes down to 184. So, and it happens again. So for the next song, 30% of 116 will sit down, that's 35, and then 20% of 184 will get up and start dancing. That's 37. So maybe you can see what's starting to happen here. There's a net change of +2 in the direction of the dance floor. So dance floor goes up by 2. The not dancing side goes down by 2. And it happens again. So you can see this is just kind of going to keep repeating itself. What's the end game here? Well, let's see. We're almost there. 30% of those that are on the dance floor will sit down. So 30% of 118 is 35. And then 20% of those that are sitting down are going to get up and start dancing. So 20% of 182 is 36. So this time the direction is a net +1 in the direction of the dance floor. So this is going to go up by 1. And then the not dancing goes down by 1. So 181. Let's try it again. We're going to keep on doing this. You'll see where it ends here shortly. 30% of the dancers are going to sit down. So 30% of 119 is 36. And then 20% of the not dancing, so 20% of 181 is 36. So what's the net change? What's a net change of 0? So, 36 will go in this direction, 36 go in that direction, net change of 0. So guess what? For the next song, it's 119 and 181. And guess what? This keeps on happening for the next song. So 30% of 119 is 36 that sit down after that song, and then those that aren't dancing, 20% of 181, 36 will get up and start dancing. So the net change is 0. So we're, and do we need to keep on doing this? Well, hopefully you can see that we've attained an equilibrium, haven't we? We can see that a dance floor equilibrium has been established here. So this dance could go on and on and on till midnight or till the sun rises or later, and we'd still have the same number of people on the dance floor and the same number of people that aren't on the dance floor because we're at this equilibrium. Now, let's ask a few questions about this and see if you can answer it. When was equilibrium established? At what point was equilibrium established? Well, hopefully, by working the problem, you can see that it was established right here at this point, and that was where the net change was 0. You had 36 going in this direction, 36 going in the opposite direction. And as you can see after that point, the numbers stayed the same on both sides of the dance. Now, what happened when we attained this dance floor equilibrium? Well, as we just said, the net change of the number of people on the dance floor or not on the dance floor was 0. Net change was 0. Those numbers after that point stayed constant. Now, does that mean that the dance ended once we got to dance floor equilibrium? No. It kept going. It just meant that the numbers on both sides were constant. So the dance was not over at that point. Did the two sides have equal numbers? Was it 150, 150 on both sides of the dance? No. So I hope that this kind of gives you an idea as to what we mean when we say equilibrium. Now, what in the world does dance floor and a dance have to do with a chemical reaction? Well, let's think about what equilibrium is not, first of all, because some students get confused when we say equilibrium. So what is equilibrium not going to be? Well, equilibrium does not mean the reaction has stopped. Just like dance floor equilibrium did not mean that the dance had stopped, well, the reaction keeps going even after we get to equilibrium. It just keeps on going. Now, at equilibrium, notice that the reactant concentrations are not necessarily equal to the product concentrations. The two sides of the dance did not have equal numbers, did they? It wasn't 150, 150. All right? It was like 181, 119. They were not the same. And that's the same thing for equilibrium. You can't expect every concentration of every single thing in the reactant to be the same at equilibrium. That normally doesn't happen. At equilibrium, all the reactant is not used up. And so there was no side that had a 0 and a 300 at the equilibrium part of the dance, right? We can expect the same thing at chemical equilibrium. We're not going to have a zero on usually any side of the arrow. So what is equilibrium? Well, equilibrium is when the rate of the forward reaction is the same as the rate of the reverse reaction. So when they're equal, that's equilibrium. And at equilibrium, your net change in concentration is zero. So the net change is zero, just like it was for that dance floor problem. Now let's take a look at this graphically. I've taken the liberty of taking the data from the dance floor problem and actually graphing it so we can see what that looks like. And so the blue line would be those who weren't dancing, so that would be here, starting at 0. And the red line represents those who were not dancing, so those will be the red line. And so at what point in the dance was movement taking place the fastest? Well, hopefully you remember from the problem, or you can see it from the graph too, that the slope is highest at the very beginning, right? At the very beginning of the dance, we had a net change of like 60 in one direction, right? Whereas at the equilibrium point, we had a net change of 0. So we can say that at this point right here, in this part of the dance, right here, or in this side, if you're looking at it from the dancer's point of view, right here at the beginning, in between song 0 and 1, that was the fastest rate of change. Now, what does the graph look like when you get to equilibrium? Well, you can see that the graph would level off. So once we got around this point right here, notice that the slope is basically 0. And so we can tell at what point we have reached equilibrium. Now, let's take a look at a chemical reaction. So this is not a dance floor problem. This is a real chemical reaction. And we're going to take nitrogen gas and 3 moles of hydrogen gas and produce some ammonia from that, 2 moles of ammonia gas. And so we have the same graph here, except we have the chemical compounds. And so once again, which of the substances here starts at a 0 concentration? Well, we can read the graph and see that that is the ammonia. It starts down here at 0 concentration. That makes sense because ammonia is the product, as you can see here. And you would expect to not have a lot of product, usually not have any product, whenever you're starting the reaction. So that makes sense that ammonia would be 0. Now, which of these reactants, and we have 2, we have nitrogen and we have hydrogen, which of those 2 is used up or depleted at the faster rate? Well, if you look at them on the graph here, you can see that the slope of the hydrogen is much higher, or it's much, I should say, it's going down a lot faster than the nitrogen is. If this is a roller coaster, hydrogen is a big drop. Hydrogen is a big drop, whereas nitrogen is not as big of a drop. So we can say that hydrogen is the one that's being depleted faster. In fact, we can actually say that hydrogen is being depleted 3 times faster. How do I know that? Well, look at the coefficients of the balanced equation. For nitrogen to hydrogen, it's a 1:3 ratio. So guess what? I would expect the hydrogen to be used up 3 times as fast as the nitrogen. Okay, so we can actually use the coefficients of the balanced equation to see the relative rates here, and we'll talk more about that later on in this lesson as well. Now, why is there more hydrogen than ammonia at equilibrium? Ammonia is a product. Why shouldn't we have a whole lot of ammonia and almost no nitrogen and hydrogen? Well, remember one of our statements about equilibrium. What is equilibrium not necessarily going to be? It doesn't mean you're going to use up all of your reactants. And so the nitrogen has been depleted to a fairly low state, but we still have some of it. And the hydrogen has been depleted, but maybe about half of it, but not nearly all of it has been depleted. And that's just what equilibrium is. You aren't necessarily going to use up all of the reactants. And if it's a reversible reaction, you're not going to use up all of the reactants. And so, in this case, we actually do have more of a reactant than we do of the product, as it turns out here in this reaction, which we call the Haber process. Now, when we talk about equilibrium and the relative amounts of products and reactants that you have in a chemical reaction, there is a numerical way to talk about that. It's called the equilibrium constant. And this is a very important number to be able to calculate. And so as we go through this course, not just this lesson, but several lessons, we're going to be calculating equilibrium constants over and over and over again, and using equilibrium constants to calculate other things over and over and over. So you really need to understand this equilibrium constant and how to calculate it. Now let's say that we had this same reaction that we had in the last slide. We're trying to make some ammonia, NH3, from its elements. And Kc, now K stands for equilibrium constant. That's what the big K is there, the capital K. And then C does not stand for constants. C kind of stands for concentration. So we'll talk about that here shortly. So the way you write the equilibrium constant is products over reactants raised to the power of the coefficient. So that means it's going to be the concentration of NH3 squared. That 2 out in front becomes the power, becomes the exponent, all over the concentration of N2, so there was the N2 there, times the concentration of H2 cubed. The 3 right here turns into an exponent whenever we write out the equilibrium constant expression. So we've just written an equilibrium constant expression for this. Now, the numbers in brackets, whenever you see something in brackets like that, that means molarity. So we've learned how to calculate molarity already, moles per liter. Well, the brackets means moles per liter. So you need to get used to that, because we're going to be calculating that quite a bit. Now let's calculate an equilibrium constant. And we're going to use this same reaction. And here we're producing ammonia. And it says a mixture of nitrogen and hydrogen gases are allowed to react and reach equilibrium at 350 kelvins. At equilibrium, the concentration of ammonia gas is 1.98 molar, while nitrogen equals 0.031 molar, and hydrogen equals 0.010 molar. Calculate the equilibrium constant for this reaction at 350 kelvins. So what we have to do is write the equilibrium constant expression first. So Kc is that same expression we just wrote. It's products over reactants raised to the power of the coefficient. And now we just have to plug and chug. We're going to plug it in and find the value of K, of Kc. So ammonia, its concentration is 1.98. So I'm going to plug that in the numerator there, and we're going to have to square that. All over, nitrogen is 0.031. So that plugs in right there. And then the hydrogen is 0.010, and that's going to have to be cubed, as you can see. So when we do the arithmetic for that, we can do the squaring and then the dividing, and we can find out what the value for Kc is, and it is 1.3 times 10 to the 8th power. That's a big number. That's the equilibrium constant for this reaction at this temperature. And you might be wondering, where are the units? As it turns out, an equilibrium constant is essentially a ratio for all practical purposes, and it is a unitless value. So equilibrium constants have no units, and so if you tend to forget to put units on there, then good for you, because you don't have to worry about units on this particular value. Equilibrium constants don't have units. So hopefully, after watching this video, you have a better idea as to what equilibrium is and what equilibrium is not, and you can write an equilibrium constant expression and calculate a simple equilibrium constant. Now, we've just barely scratched the surface. In the next video, we're going to learn how to write some more equilibrium constant expressions for more complex reactions, And we're going to figure out what the equilibrium constant means, and we'll get a lot more practice on this. If you'd like to watch that video, then make sure that you subscribe to my channel so you don't miss a thing. I'm Jeremy Krug. I've been teaching AP Chemistry for over 20 years, and I want to make sure that you get a 5 or get an A on your class or in that test. So join me again on my next video where we can learn some more chemistry together.